Good afternoon, everybody. Hope you can hear me even clearer without mask. As you can see on this slide, it's probably a lot of things you have seen on slides from other companies as well. We are a very big company. We have very deep division of labor, as you can see from this presentation, because who else would have 3 speakers for 20 minutes? And when we look into the past and look at IT and rollout of IT inside the company, most of IT projects, they don't fail because the IT is bad. They fail because those who understand the business for which the IT is and those who understand the IT and the programming, they don't match. And whenever we have a new technology like, for example, in this time, and the quantum computing, it's the same thing. Especially now, I don't know how this will be in future, but now for quantum computing, one of the biggest problems is to make the right model so that your computer can then use a second or so to come up with all the answers. The creation of the model beforehand so that your problem really is in a model so that the computer works with it. That's the trick, and that will take much more time than the calculation itself. So if you look at all these things that were even inside our company, and we're only making cars, at lots of places, quantum computing can make a huge difference for us. And to leverage this, to be possible to do this, we have to make sure that whenever quantum computing is ready, we are ready as well. And we are ready means that all these departments that could leverage it, that have an advantage of this, that they are prepared. And our way of doing this is going through the company and see who could be affected, who could have advantage of this, and getting them all into the quantum computing team and understanding the way these models are generated and understanding which quantum computers are optimized for their tasks. So that when these computers get in a range where we say that they are optimized and they are now good enough to calculate our problems, we are already there with our models, and then we can leverage these things right at the places where they are needed inside the company. So currently we on a systems level engineering, we're trying to prepare the company for all these things that are coming up within the next few years. And from telling you now from how we do it inside the company, let's go into the details, and Elvira will tell you about how we are going to do that.
Yeah, thank you very much. I'm based actually in Munich, and that's why it's double happy for me to share the stage with our Japanese colleagues from the Tokyo office. Yeah, I could probably move a little bit before to this slide. So the initiative, quantum computing initiative at BMW started back in 2017. From the beginning, it was an object of what we call technology scouting. When we tried, or our specialists, we tried to screen it and to map its potential for future BMW activities. So since 2017, we're matured a little bit, and we feel ourselves a little bit more ready to go into a deeper exploration and to expand the domain of applications that from the beginning was only optimization tasks. And now we can cover, let's say, 5 application domains with more than 50 use cases that were pre-identified. This is the chemistry and materials to design better battery electrodes or hydrogen fuel cell catalyst and many more applications. Optimization, of course, because I would say any company, industrial company especially, can summarize its activity in the range of optimization tasks from both R&D and operations perspective as well. Machine learning, we started actually also quite early with the classification tasks for automated quality assessment. But now we go a little bit deeper, and I will show you later that we are considering as well the generative modeling possibilities. Finance, we have couple use cases on finance as well. And last but not least is numerical simulations of physical processes, crash simulations, thermodynamics, aerodynamics, heat transfer in batteries and engines, something that we need to accelerate in order to go towards zero physical prototype in the production. And now, let me just give you a couple concrete examples of what we do, what we try to do and explore. And let's start with chemistry, which is nowadays considered as one of the most native applications and a lower hanging fruit. So development of new materials is actually a very complex process that happens in many stages. And the digital modeling or the virtual experimentation can be considered as a sort of intermediate filter between the initial, I don't know if I can do some, no, I can't, sorry. Between the initial, let's say, empirical guess when you try to predict based on the empirical knowledges some of the good candidate materials, and you can have billions of them. And the very final stage when you synthesize physically in the lab all those predicted materials and try to test them manually, it takes a lot of time, resources, and also human hours. So you can easily imagine that if we could have a very good predictive filter, this virtual modeling filter, we could reduce the number of candidates to synthesize in the laboratory and as a result to economize on resources and time. Unfortunately, classical numerical solutions or exact classical numerical solutions, and you've heard about it during the both days of the conference, we don't scale. So we can compute like very tiny systems with like a very limited number of particles of electrons, and we can go beyond that. Classical computational chemistry actually much better than that. So we have also available the range of approximate solutions that we actively use. But the problem of those solutions is that we don't work for all the systems. And specifically, we don't work for the strongly correlated system, which unfortunately for us is also example of batteries, electrodes, hydrogen fuel cell catalysts, materials for carbon capture, and many others. And that's why we hope that quantum computing could enhance this process of new materials development, providing the fast and also predictive numerical simulations. Here I give you on the right side some examples of how we think, or the community thinks, this enhancement might be. So you can speed up the exact solution. You also can improve the accuracy of large-scale simulations. And we try to explore all these directions within different collaborations that we have together with different partners, but also with research institutions. We co-founded 2 endowed chairs with Technical University of Munich and Aachen University, and also within the industrial consortia that becomes very popular, and fortunately right now. One concrete example that I would like to propose you is the example that we treated very recently of hydrogen fuel cells catalysts. So as you probably know, hydrogen is considered as a very promising energy source because of its regenerative nature. The only reason why it still loses, let's say, in popularity to the electric batteries is because we constantly lose in energy efficiency on each single step of the hydrogen value chain, starting from green hydrogen production, transportation and storage, and ending up by the fuel cells. So as the end user, we decided to focus on the latest one. In the typical example of a fuel cell, you have the anode on the left side, the electrolyte in between, and the cathode on the right side, or catalyst. So the hydrogen is a fuel set to the anode, the electrolyte, they conduct their protons, and then the main reaction, or the most complicated reaction, called oxygen reduction reaction, happens on the surface of cathode or catalyst. So being one of the most fundamental reactions, the oxygen reduction reaction mechanism is still very poorly studied. And this can probably explains why, like, since decades, someone discovered that platinum or some other noble materials, they can be very good for catalysts, but no one actually knows why, by which exactly properties, and that's why in 2022 we still use loads of platinum to produce catalysts, and we don't know how to find better substitutes. So we really hope that quantum could help us to discover a little bit deeper this mechanism of oxygen reduction reaction. And we decided to try it with the available means right now, or at least reproduce some data or prototype some data that are available right now empirically, and to see what our level of understanding of quantum computing theory can provide us with right now. The mechanism of this reaction was quite complicated. I already mentioned that. It happens in the many stages, and that's why we focused on its most slowest kinetic step and one of the biggest driving force, dissociation of the oxygen on the platinum. So we reproduced the results that we could find available, the reference results that we could find available in the literature. You can see them actually on the left corner of the slide. Those results were released last month. You could find the presentation in the internet as well. Because I want to cover a little bit more applications, I won't stop on that. But basically, it made us also discover some very important conclusion that you need to take into account the dynamical correlations that classical approximate method don't take, unfortunately, into account. And basically, that's why solution without those correlations, we can come up to a completely opposite sign of energy, which is not really what we want. And also, even if this small cluster, we actually had many slab, it's still pretty massive thing to treat it fully on a quantum computer. You still need to use a lot of pre-processing using the classical chemistry solution, which once again are very good. So you can use all the range of fragmentation embedding techniques in order to localize the most complicated part of your molecule, which in our case was interaction directly with the oxygen, to treat it locally quantumly, and then the rest of the part, which is much more easier, using the classical solutions. So these are more or less the conclusions that they have. Once again, the results are available. You can find them in the literature. We worked together with an amazing team of Cambridge Quantum Computing, or now it's Quantinum, who provided the expertise on the quantum computing algorithms. There was also experts on the hydrogen fuel cells involved and quantum computing team involved on BMW side, and we continue this collaboration. Just very quickly, two other examples. The example of numerical simulation of physical processes, I already mentioned a couple of them, like crash simulations, aerodynamics design, aeroacoustics, or heat propagation in batteries and fuel cells. All those problems can appear actually in any industrial company, and all those problems are reduced to solving very complicated partial differential equations. Unfortunately, the modern classical methods for solving those equations are rather compromised between the accuracy and cost, and that's why what happened in reality, our engineers have very perfect, let's say, digital models, but when you come to the production, it's actually not that was predicted, and that's why you need to increase the number of physical prototypes and tune them manually in order to obtain the desired results, which is not really sustainable and efficient. Why this process is so much complicated? I mean, why the classical solutions are so bad? Well, first of all, because the analytical solutions usually for real-life cases doesn't exist, so you need to somehow pass from the continuous problem to a discrete one. At the very first stage, you discretize your, let's say, stationary model onto many elements, and when I say many, it can up to billions, well, 100 millions, let's say, for the realistic models. And you need to solve these 3D stationary models that involves the inversion of very large sparse matrices. Once you're done with a stationary problem, you need to do the time evolution. And sometimes for the processes, when dynamics propagates very fast, you need to consider very tiny time steps. If you go to our engineers, we could tell you sometimes the numbers like down to 10 minus 6 of second. That means that to simulate 1 second of a real process, you need 1 million time steps. And on each time steps, you will solve a stationary problem. And even after you've done all this, it was only done for the given design. So you need to vary the parameters of your design in order to find the optimal configuration and repeat the steps 1 and 2. So we understand the complexity of this problem, and we want to tackle right now. Lutz already mentioned that actually the algorithms, for instance, are not ready at all. This is not the native problem, and that's why we understand how important to investigate it right now and what we do in collaboration with Pascal, the European Research Center on Scientific Computing, and together with the University of Erlangen. And very last one case is the generative modeling and design. So deep learning solutions are very well known for helping us to invent the designs of the products which are very original, but also to incorporate some important mechanical properties like aeroacoustics, aerodynamics as well, to reduce the weight of the components while preserving all the safety requirements. Unfortunately, the classical GANs or generative adversarial networks, they have many fundamental challenges that we don't know how to solve, but there are some ways how quantum computing could be of help for that. And that's what we explore together with the Technical University of Munich and within the consortium, industrial consortium Q2B. So this was the last slide. Just before ending up, a very, very short remark is that for instance, we are not anymore at the discovery phase. We are already at the engineering phase. We have this luxury to have such big landscape of quantum computing providers who gives us all the tools and possibilities to train ourselves to develop the very first prototype and to prepare ourselves and our applications when the quantum computers will be ready. Thank you very much.